gases. We'll have a look at the processes that allow us to change between the states. And then finally, we'll have a look at why some materials have different temperatures at which they change state. So let's first define what our three states are. The first we're going to look at is a solid. So we define things to be solids if they stay the same shape and their volume stays the same unless a force acts on them. So that statement is what we use to describe a solid. In terms of what it looks like at an atomic level, we have very strong forces between the atoms, which means the atoms are packed closely together, and we can see that they're in a very regular pattern. So they do move, but they just vibrate about a fixed position, and they vibrate at pretty low speed. So that's our description of what solids are. Let's move on to liquids. So a liquid is something that will change their shape to match whatever their container shape is, but will still keep a fixed volume. So in terms of what that looks like at an atomic level, we still have pretty strong forces between the atoms, not as strong as in solids, but still pretty strong. So the atoms are still close together, but they are now free to move relative or move past one another, which means they are arranged in a random manner. We can't predict exactly where an atom will be at any particular moment in time. And the atoms are actually moving at higher speed in a liquid, so they have more energy. So that's a liquid. Let's finish off by looking at gases. So a gas can change both their shape and their volume, so they'll expand or contract to fill their container. So in terms of at an atomic level, we have very weak force between atoms, and this means we've got atoms spaced very far apart. And because they're all over the place, they are in a completely random arrangement. We can't predict where atoms are, but the atoms of a gas have very high energy, higher than a liquid, and they're traveling at higher speed because of that. So are three states of matter. I should throw in at this point there are more than just these three. You might have heard of things like plasma, and if you go into quantum physics there are way more, but these are our three classic states of matter that we start off by learning about. So let's now have a look at what happens when we take a material and we heat it or we cool it. So water, if we supply thermal energy at a constant rate, has a graph that looks like this. So we've got temperature against time. And we can see to start with, between A and B, as we heat it, the temperature rises. Then we've got a section where the temperature stays the same. Then we've got the temperature rises again. We've got temperature stays the same between D and E. And then temperature rises again. But the whole time, it's being supplied with thermal energy, which raises some quite interesting questions. So that's if it's being heated, and we have words we use to describe the two particular transitions. So when we're turning from a solid into a liquid, from B to C, we call that melting. And when we're going from D to E, turning from a liquid into a gas, we call that boiling. Now, if we cool a material, it comes the other way down the graph. So if we cool it, it first decreases temperature, then it stays the same as it turns from a gas into a liquid, which we call condensing. Then the temperature decreases again, and then when we reach the melting temperature, it solidifies at that point, and then it starts decreasing temperature as a solid. So those are our processes that we have going on when we either heat or cool a liquid. So at this point, there should be quite a few questions occurring to you from what you're seeing here, because to most people, when they first meet this topic, this doesn't make sense at all, because they're like, we're heating a material, why on earth is its temperature not changing? So that's most people's first question, and it's a really good question to be asking. So why, when we're changing state, doesn't the temperature change? And we'll have a look at that a bit later on. And now, another question you might ask, those of you who look at this in a little bit more detail, why is this D to E process longer than B to C. What's going on there. And then thinking about this in terms of water and starting to think of how this applies, hang on, if it's according to this graph, water changes into a gas at 100 degrees. So how on earth does our sweat evaporate at only 37 degrees? And this question that we're going to address next, and we're going to look at a slightly different process called evaporation. Those were the processes that we would typically get when we're heating or cooling water. Let's have a look at another process that can happen. So, the first thing we need to understand is what actually is happening when a material is changing state. So essentially what we're doing is we're supplying thermal energy to the material, and if we can give the atoms enough kinetic energy, they can overcome the forces between the atoms and they can change state. So that's the first thing that we need to know. The second thing we need to know is not all atoms in a material have the same kinetic energy. So some have a larger amount, some have a smaller amount, and those of you going to do A-level physics and chemistry will learn how we actually deal with that and model it. But for now, we'll just satisfy ourselves with knowing the atoms don't have the same kinetic energy. So some below 100 degrees will have enough energy to overcome the forces and escape. And that's a process we call evaporation. So boiling is if it's happening at 100 degrees or at the boiling point. Evaporation is if it's happening at a temperature below the boiling point. And that can happen because some atoms will always gain enough energy to be able to escape. So, okay, so that's how sweat actually, how we are losing sweat. But why do we? So the key is sweating is a process to deal with the scenario when we are too hot. So we want to keep our body temperature at 37 degrees because if it goes above that, it starts affecting all the different chemical processes we've got going on in our body, which work at an optimal rate at 37 degrees. So we sweat to cool ourselves down. So as the water is evaporating from our skin, what's happening is thermal energy from our body is being transferred to those water molecules, and some of them are gaining enough kinetic energy to escape into the air around us through a process called evaporation. So this is why sweating cools us down, because it's taking thermal energy from inside our body and using it to evaporate the water. That's why we actually end up sweating. So this question might be, well, how can we actually increase the amount of energy we lose? If we're very hot, we want to be losing a large amount of thermal energy. So that is something that would naturally happen anyway. So if we are hotter, we will transfer more thermal energy to water, and therefore we can increase the rate at which evaporation is occurring because more atoms will be gaining enough kinetic energy to escape. So that's one thing we can do. Another thing we can do is have a larger surface area, which means that there will be more water molecules sitting on the surface of our skin, so we can have an increased rate of evaporation from that as well. Another thing that can affect our ability to sweat is the humidity of the air. So humidity is the amount of water that's in the air. So high humidity means there's a lot of water vapor in the air. Low humidity means there's not very much. So there's a lot of water in the air already. It makes it harder to evaporate water because the air doesn't necessarily want the water in it. So humid air actually decreases the effectiveness of sweating. So if you go to somewhere like a rainforest or other places on Earth which are very humid, sweating becomes ineffective as a means of losing thermal energy, which can be problematic. The last thing that can change how effective we can sweat is how fast the air is traveling. So if you're hot, you might use a fan, for example, to help cool you down. And the way this works is that when you evaporate water off your skin, that increases the humidity of the air around your skin. So by blowing that air away, then we replace it with air which is at lower humidity, which is more effective for evaporating water. So that's why we use fans, because airspeed is another factor which can affect evaporation. Okay, so looking at these four things, those of you studying biology as well might have noticed that these are the same factors that affect the rate of transpiration in leaves of plants. And you would be exactly right to be making that connection there. So it is exactly the same process. Transpiration is very much like plant sweating, effectively. But for plants, that's a bad thing. We as humans want to sweat because we're trying to cool down. It describes evaporation and how we can change the rate of evaporation. Let's finish off by having a look at why some materials have higher melting or boiling. So we've talked quite a lot about how in the different states of matter there are different forces between atoms, but it's the same for different materials. So metals have bonds called metallic bonds, which is keeps them fixed in their structure and gives metals very high melting and boiling points. Water has a type of bonding called hydrogen bonding, which is also a strong bond, which is why it takes a lot of energy to change the state of water. And any given material have these things called London forces, or sometimes called van der Waals forces, which attract atoms together. But those ones are very weak. So if you're a material that only has these London forces, you will probably be turning into a gas at a very low temperature. So things like oxygen, nitrogen, for example, would have very weak forces, so they don't need much energy to evaporate. Metals have very strong bonds, therefore they need a lot of energy to change their state, which is why most metals are solid at room temperature, apart from mercury, which is a liquid. So if you have a large melting or boiling point, that means the forces between atoms are much stronger, so the atoms need much more kinetic energy to break those bonds. That's the way to kind of think about it there. So a question you might have following on from this: what on earth are these metallic hydrogen bonds or London forces? Really good question. I'm glad you're asking yourself these questions, but I am going to leave you on your own for that one. You will need to take some A-level physics or chemistry or a similar level course, or do some of your own research to find out about those things. It's not part of the GCSE course, so I'm not going to go into it at this stage, but please do go and have a look at those things. They are very interesting things to go away and research. So that's where I'm going to leave it for today. So at this point, what you need to be able to do is describe the key characteristics of solids, liquids, and gases. And then you need to talk about the processes that can happen to a material as you heat or cool it. And then finally, we looked at the end, you should be able to explain why some materials have a higher boiling or melting point than others. And if you can do those things, that's the time to stop, because we've finished working on this stuff for now. So thank you very much for taking the time to watch this video. I hope you found it useful. If you have any questions, please feel free to comment and ask me. I'll try and get back to you as quick as I can. But as I said, thank you for taking the time to watch this video.